Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. So today our group will present about composite testing and critical analysis of literature review. So our group consists of myself, Muhammad Hafiz bin Nordin, and also three other group members, which is Aizat bin Abdul Rashid, Muhammad Jeffrey bin Mohammed, and also Muhammad Aiman. So we're moving on introduction. Tensile impact test, access composite. For application like aerospace and automotive, tensile impact test is crucial for evaluating the mechanical properties of composite materials in the construction especially. And this test measure properties like UTS, ultimate tensile stress, strength, modulus elasticity, showing that synthetic composite such as glass, fiber, epoxy is excel in strength to weight ratio and stiffness, while natural such as knauf and bamboo are eco-friendly and cost-effective. So for impact tests using method like Charpy and IZOD, excess energy absorption, we put it sudden loads with synthetic composite which offer good resistance but brittle failure risk. And for natural composite, we are provide higher energy absorption with lower strength. So these tests ensure the structural reliability and prevent failure under varied load condition. For problem statements, the first one is there is lack of comprehensive comparison between synthetic and natural fiber reinforced polymer composite, particularly considering their tensile properties and environmental sustainability. The second one is variability in mechanical performance due to factors such as fiber orientation, volume, and matrix compatibility in natural composite is not really well understood. And lastly is limited research has been conducted on improving the interfacial bonding of natural fiber with polymer matrices to enhance their tensile mechanical properties for broader application in the future.
Alright, for the objective, we have three objectives in this literature review. The first one, to analyze and compare the tensile mechanical properties of different polymer composite, including glass fiber epoxy, carbon fiber epoxy, knauf fiber polyester, and bamboo fiber polyester. And the second objective is to investigate the influence of fiber types and metric property on the tensile strength, Young modulus, and elongation at the break of polymer composite. And the third one is to identify potential application for natural fiber reinforced polymer composite based on their mechanical performance and sustainability. So we move on to the literature review. Glass fiber epoxy. In the glass fiber epoxy, the tensile strength range from 450 to 600 megapascal, providing excellent load bearing capability. And the Young modulus, the range is between 25 to 35 gigapascal, offering high stiffness for structural integrity. And the key features: strong fiber matrix bonding ensure efficient stress transfer. Applications ideal for aerospace and automotive industry. And the performance influence fiber orientation and volume fraction significantly affects mechanical properties. And the research finding studies highlights the importance of interfacial bonding and its effects on tensile performance. So this is the structure of glass fiber epoxy. We can see that epoxy and the glass fiber combined together at the part A, and the part B we have meso scale, micro scale, and nano scale. And the second literature review is about carbon fiber epoxy. And the tensile strength, the range of carbon fiber epoxy between 900 to 1100 megapascal, making it one of the strongest composite. And the Young modulus between 70 to 120 gigapascal, offering superior stiffness for high performance application. And the key features: high strength to weight ratio, exceptional load transfer, and resistance to environmental degradation. And for the application, it's also used in aerospace structure, sport equipment, and automotive part. And the performance enhancement Further improvement with optimized fiber alignment during curing conditions, and the cost consideration. Higher performance comes at a higher cost, limiting its widespread use. So the next part is the structure of carbon fiber. What we can consider in this in the making of carbon fiber is sizing agent and the carbon fiber itself, and then we have acting force, and then explosive resymmetry, and then we will make the carbon fiber composite material.
Exploited literature review of Kena fiber hashtag polyester tensile strength ranges from 120 to 180 megapascal, providing moderate strength for non-constructional applications. Young's modulus between 5 to 10 gigapascal, reflecting the natural fiber's relatively lower stiffness. For the key features, biodegradable and environmentally friendly, making it a sustainable alternative to synthetic composites. Applications suited for packaging, automotive interiors, and other non-structural applications. Performance enhancements, chemical treatments improve fiber matrix bonding and increase tensile properties. Adverse sustainability, fast growth, low cost, and carbon dioxide absorption make Kenaf an ecologically beneficial material. As for the structure, the resin matrix is a middle and the Kenaf fiber sandwich between. As a reference literature review, it is bamboo fiber polyester. Tensile strength ranges from 100 to 150 megapascal, suitable for lightweight applications. Young's modulus between 4 to 8 gigapascal, indicating moderate stiffness. Key features: high environmental benefits, including fast growth and low pesticide requirements. Applications often used in construction, furniture, and low-cost building materials. Performance influences properties depend on fiber preparation methods such as alkali treatment for better bonding. Challenges limited by high moisture content in natural bamboo, requiring effective extraction and treatment methods. As for the structure, it starts from fast-growing bamboo forest into bulk bamboo and into vascular bundles and matrix, cell wall layers, fibril, microfibril structure, crystallized cellulose molecular chain structure. As for the literature review comparative analysis, glass fiber epoxy provides a balance of high tensile strength and stiffness ideal for structural use in demanding environments. Carbon fiber epoxy, superior tensile strength and stiffness but more expensive, suitable for high performance applications only. Thinner bamboo fiber polyester offer lower tensile strength but are most suitable, cost effective and biodegradable, making them ideal for eco-friendly applications. Performance variability, mechanical properties are influenced by fiber orientation, matrix properties, and treatment methods. Fiber matrix bonding, synthetic composites benefit from strong bonding, while natural fibers require treatments for enhanced compatibility with matrices. Design and applications, proper selection of composites depends on the required strength, cost, environmental impact, and specific application needs.
Next, we move to the methodology. So in methodology, we focusing on fabrication and testing of the composite material. So for preparation of tensile specimen, UPE, unsaturated polyester, and epoxy resin were employed as a material. For the natural fiber, including kenaf and bamboo, such treatment were adopted to enhance a fiber matrix adhesion. The most widely adopted treatment was alkali treatment to remove non-cellulosic materials such as lignin and wax. This was not subject to the surface treatment because the synthetic fibers such as glass and carbon have a natural good adhesive with the polymer matrix. For the fabrication of techniques, filler of 48 nanometer particle with higher elastic modulus, wear resistance and thermal sensibility. So the preparation, filler dry at 60 Celsius for 1 hour, epoxy at preheat at 65 Celsius to reduce our viscosity. So next, we mixing and curing. Stir at 65, also stir at 65 for 1 hour. Hardener at to stir for 15 minutes. Mold and cure at 120 Celsius under 50 megapascal for 3.5 hours. Slow cooling to minimize residual stress. Next, for the tensile test. For tensile testing, specimen were cut into a rectangular blank using a diamond blade saw, and edges with a finish with emery paper to avoid surface flaw. The tensile test applies an unaxial load to the specimen and measure the response of material as it stretched until failure. The purpose the purpose of this test is to determine the monotonic mechanical properties of the composite material. Among the monotonic mechanical properties that can be obtained from the tensile test are yield strength, ultimate tensile stress, and Young modulus. The ultimate tensile stress is measured to determine the maximum stress that material can withstand when the stretch or pull before necking occur, which is localized reduction in the cross-sectional area. For the impact test, an impact test is a type of dynamic test that applies sudden load to a specimen and measure the amount of energy absorbed by the material before it breaks. The most common types of impact tests are Sharpie and IZOT, which use a pendulum hammer to strike the specimen at a specific location and angle. The impact test is useful for evaluating the toughness, ductility, brittleness of the material, especially at a lower temperature with high strain rates. The purpose of impact test was to evaluate the material toughness, which refer to the amount of energy material can be absorbed before fracturing. Impact strength was measured by recording the energy absorbed by the specimen during the impact, typically expressed in joules. The result provides insight in the material fracture behavior, including the resistance to the brittle failure and its ability to deform under stress. So next, move to the comparison. So for the comparison, tensile test and impact test, what is measured? For tensile test, material strength under a load and steady load. For impact test, material ability to absorb energy during the sudden force. For load type, in tensile test, gradually and steady. For impact test, sudden and high speed. So the test in tensile test performed using a universal testing machine with a control loading rate. For impact test, use a pendulum-based equipment such as Sharpie and IZOT impact tester. For tensile test, for structure that need handle long-term loads, and impact test for parts that face sudden impacts or crashes.
We move next to results and discussion. Glass fiber epoxy with aluminum oxide particle contents. Tensile strength decreases gradually with increased aluminum oxide contents. Young's modulus increases up to 10% filler content, then decreases slightly. Elongation at failure decreases with increasing aluminum oxide content. Flexural strength and modulus increases with up to 10% aluminum oxide, showing a 23% and 78% improvement, respectively, compared to unfilled composite. Beyond 10% filler content, flexural strength and modulus decrease. Moving on to benzyl fiber polyester, tensile strength and modulus decreases with higher fiber loading in FBF, R&R. Optimal fiber content, 30% fiber content by mass for the best balance of tensile strength and modulus. Tensile strength increase, PFGC composites show continuous increase in tensile strength with fiber content from 10% to 50%. Comparison with sisal and Joule composites. Membrane composites exhibit 1.9 times higher tensile strength at 0.4 volume fraction. Carbon fiber composites. Tensile strength meter 1 shows 898.3 megapascal, meter 2 shows 759.8 megapascal. Impact of processing low pressure during molding results in uniform components and reduced ductility. Toughening increased tensile and flexural strength at room and cryogenic temperatures with HPT treatment. Surface treatment, grafting with hyperbranch polymers increases interfacial shear strength and impact strength. Canal fiber composites. Tensile strength, highest strength observed at 30 WT% with 20 mesh filler. Fiber composite effects, 40 mesh filler at 40 WT% increases tensile strength to 15.5 megapascal due to better filler matrix bonding. Young's modulus increases with higher fiber loading supporting larger loads. Polymer additives, NATP and CNTS improve strength, but CNT agglomeration can reduce effectiveness. Temperature effects, PLA-based composites show lower tensile strength at higher temperatures, suggesting brittle behavior. Finally, canal polymer composites. Tensile strength epoxy composite with higher canal loading up to 15 WT% show reduced performance due to poor matrix temperature. Performance at high fiber contents beyond 15 WT% composite performance declines and mechanical utility is hindered. Comparison, treated canal composites outperform untreated composites at lower loading 20 WT%, showing better adhesion and tensile strength.
So for conclusion, tensile and impact tests are crucial for understanding the mechanical behavior of composite materials under various loading conditions, adding in the material selection and design. Tensile tests measure properties like tensile strength, Young modulus, and ductility under steady, unaxial loading, highlighting the high strength and rigidity of synthetic composite, such as carbon fiber, for demanding application, while natural fiber composite like knaf and bamboo offer eco-friendly, cost-effective alternative with moderate strength. The impact test assess the energy absorption and fracture toughness under dynamic loading, showcasing the superior impact resistance of synthetic composite like glass and carbon fiber for high-performance users, while natural fiber perform well in lightweight, sustainable application with lower demands. Together, these tests provide comprehensive understanding material behavior, enabling engineers to optimize composite performance to meet specific strength, economic, and ecological goals. So that's all. Thank you.